Welcome back to our journey through the fascinating, and sometimes frustrating, world of soil mechanics. In Module 1, we covered the origin of soils and their basic phase relationships, void ratio, porosity, specific gravity, and so forth. We saw how soils are formed, what they are made of, and why their structure matters. Now, in Module 2, we will focus on how we classify soils, how water flows through them, and how laboratory tests help us quantify these properties. Think of this as the practical engineer's toolkit, the methods that allow us to take a handful of soil from a site and turn it into numbers, categories, and performance predictions. Let's start with classification. 1. Soil classification. The first question any engineer should ask about a soil sample is, what am I dealing with? Soil classification systems give us a common language to describe soils in a consistent and predictable way. Broadly, classification aims to organize soils into groups with similar engineering behavior. Allow engineers to predict performance from classification data. Provide a shorthand description for communication. Two major types of classification are used in geotechnical engineering. Textural or particle size classification, based purely on grain size distribution. Engineering classification systems, combining grain size with plasticity characteristics. 1.1 Textural classification. This method looks at the relative proportions of gravel, sand, silt, and clay in a soil sample. The U.S. Department of Agriculture (USDA) classification, for example, divides soils based on the percentage of each size fraction. A triangular diagram, often called a textural triangle, is used to find the soil's name based on its composition. Typical particle size ranges. Gravel, larger than 2 mm. Sand, 0.075 mm to 2 mm. Silt, 0.002 mm to 0.075 mm. Clay, smaller than 0.002 mm. 1.2 Engineering classification. Here, the most widely used systems are Unified Soil Classification System, USCS, common in civil and geotechnical work worldwide. ASHTO system, used heavily in highway and pavement design. The USCS combines particle size distribution with plasticity, using Atterberg limits, to assign a two-letter group symbol, for example, GW for well-graded gravel, CL for low plasticity clay, and so on. 2. Atterberg limits. The Atterberg limits are a set of water contents that define the boundaries between different consistency states of fine-grained soils. They are essential because clay soils behave differently at different moisture levels. 2.1 The three main limits. Liquid limit LL, the water content at which the soil changes from a plastic to a liquid state. Plastic limit PL, the water content at which the soil changes from a semisolid to a plastic state. Shrinkage limit SL, the water content below which no further volume change occurs as the soil dries. 2.2 Plasticity index. The plasticity index, PI, is simply the difference between the liquid limit and plastic limit. Pi equals LL minus PL. It measures the range of moisture content over which a soil remains plastic. A low PI, e.g., 7, indicates a soil that transitions quickly from brittle to liquid. A high PI, greater than 20, suggests a highly plastic, expansive clay. These limits help classify soils in the USCS and predict shrink swell potential. 3. Particle size distribution. Grain size analysis tells us the range and proportion of different particle sizes in a soil. This can be done by sieve analysis for coarse soils, sand and gravel. Hydrometer analysis for fine soils, silt and clay. The output is typically a grain size distribution curve, from which we can determine uniformity coefficient, indicating how well graded a soil is. Curvature coefficient, indicating the shape of the distribution. A well-graded soil has a wide range of particle sizes and usually compacts well, while a poorly graded soil has uniform particle sizes and may be less stable. 4. Flow in soils, seepage and permeability. Water movement through soil affects everything from foundation stability to slope safety. In geotechnics, we refer to this as seepage. 4.1 Permeability. Permeability is a measure of how easily water can pass through soil pores. Coarse-grained soils like gravel have high permeability. Fine-grained soils like clay have very low permeability. Permeability depends on grain size and distribution, void ratio, soil structure, degree of saturation. 4.2 Darcy's law. Flow in soil is commonly described by Darcy's law, which states that the discharge rate is proportional to the hydraulic gradient and the permeability of the soil. From this, we see why permeability tests are so important. They give us the K value used in seepage calculations for dams, retaining walls, and dewatering systems. 4.3 Seepage in practice. Seepage can cause uplift pressures under structures, piping, internal erosion in dams and embankments, loss of stability in slopes. Controlling seepage often involves cut-off walls, drains, or filter layers. 5. Laboratory test. Let's connect the theory with the practice. For each property we've discussed, there's a standard test. 5.1 Atterberg limit. Liquid limit test, Casagrande cup or cone penetrometer. Plastic limit test, rolling soil threads by hand. Shrinkage limit test, measuring volume change on drying. 5.2 Grain size analysis. Sieve analysis, stack of sieves, mechanical shaker, weighing retained fractions. Hydrometer test, sedimentation principles for fine particles. 5.3 Permeability test. Constant head test, for coarse soils. Falling head test, for fine soils. These tests help us calculate the coefficient of permeability and apply Darcy's law. Closing remarks. With the completion of this module, we've now covered how to classify soils accurately, how to measure their plasticity and grading, how to evaluate their flow behavior through permeability testing. Taken together, Module 1 and Module 2 give you a complete introduction to soil mechanics fundamentals, enough to approach any site investigation with confidence. In real engineering, these concepts combine during site characterization, design of foundations, and evaluation of earth structures. They are not just academic, they are the difference between a stable project and a costly failure.